With Google achieving quantum supremacy, I thought I'd make a few videos going over post-quantum cryptography. That term supremacy or quantum supremacy is a strange choice of words to me, or at least the word supremacy itself. To super simplify, all that means is Google was able to get a quantum computer to do something that regular or classical computers cannot. And before I read any part of this Wikipedia article, I should just say that basically, all we have to do to make sure our cryptography is good against quantum computers is make the key links longer. And I'll let this article give you more details about that. So to start, post-quantum cryptography is distinct from quantum cryptography, which refers to using quantum phenomena to achieve secrecy and detect, that's weird, but detect eavesdropping. If I'm talking about quantum cryptography, I'm talking about encrypting things, not detecting eavesdropping. So not sure where they're going with that, and there is no citation there for me to dig into. So what is this referring to? Post-quantum, quantum-proof, quantum-safe, quantum-resistant? This refers to cryptographic algorithms, usually public key algorithms, that are thought to be secure against an attack by a quantum computer. As of 2019, this is not true for the most popular public key algorithms, which can be efficiently broken by a sufficiently strong quantum computer. The problem with currently popular algorithms is that their security relies on one of three hard mathematical problems: the integer factorization problem. And before I read the other two, I know my question is going to be this: what are the three hard math problems involved in encryption? In this case, we're talking about public key encryption, but basically, problem number one is the factorization problem. Problem number two is the discrete logarithm problem, or we could be talking about the elliptic curve discrete logarithm problem. All of these problems can be easily solved by a sufficiently powerful quantum computer running Shor's algorithm. The question is, what algorithm would a quantum computer need to run to solve these hard problems? And the answer is Shor's algorithm. Maybe I could do a separate video on that. But for now, even though current publicly known experimental quantum computers lack processing power to break any real cryptographic algorithm, many cryptographers are designing new algorithms to prepare for a time when quantum computing becomes a threat. This work has gained greater attention from academics and industry through the PQ Crypto Conference series since 2006, and more recently by several workshops on quantum-safe cryptography, hosted by the European Telecommunications Standard Institute, ETSI, and the Institute for Quantum Computing. In contrast to the threat quantum computing poses to current public key algorithms, most current symmetric cryptographic algorithms and hash functions are considered to be relatively secure against attacks by these computers. While the quantum Grover's algorithm does speed up attacks against symmetric ciphers. Okay, let's break that apart real quick. So according to this article, what is Grover's algorithm doing? And it is speeding up the attack of symmetric ciphers. You'll need to remember that public key encryption is all about asymmetric cryptography. In terms of brute forcing symmetric cryptographic keys, it looks like Grover's algorithm would speed this process up. So depending on the key length, maybe instead of 100 years, it would take 20 years to solve, which is still a very long time. And I'm totally guessing with those numbers, so don't write those down. But the next part of the paragraph goes on to say that doubling the key size can effectively block these attacks. So like I said at the beginning of the video, just make bigger keys and you'll be okay. Okay, so that was it for this video. Just a real quick intro to what we're about to learn, and therefore I will go ahead and go over the contents. We'll have an algorithms section, so I look forward to just reading through each of those algorithms. Then we can go into security reductions. Not sure if I'll go so far as to look at these comparisons. But in terms of the article, it finishes with that, and then talking about forward secrecy, open quantum safe project, and implementation. Implementation is so short. Let me go ahead and just read it real quick. It says, one of the main challenges in post-quantum cryptography is considered to be the implementation of potentially quantum safe algorithms into existing systems. There are tests done, for example, by Microsoft Research, implementing PICNIC in a PKI, that's a public key infrastructure, using hardware security modules. So Microsoft's solution is to use hardware. For our question though, let's first start with what is PICNIC, like we really want to know what that means. And then the easy to answer question is, what is Microsoft's research's approach to implementing safe algorithms? The answer would be using hardware modules. So I assume this right here is a picture of one. It looks like a typical card that you would put into a motherboard. Except this one, I'm not seeing any slots except, I can't move the mouse to show you, but if you look there to the left. But that's Microsoft Research. There's also test implementations for Google's New Hope algorithm done by HSM vendors. HSM stands for Hardware Security Module. So there's two pictures to end the video with. Like I said, I just wanted this to be a real short intro, so we got 5 questions to answer right here.